So welcome to the 8th lecture of module 6. So today this lecture is actually a continuation of lecture number 7, where we discussed about thermocouples. So thermocouples, although they are widely used, they have their own disadvantages. One is that they have lag, that is the output, they respond with some lag to changes in temperature. That is one thing. Then we have seen that we have used millivoltmeter as part of the circuit along with thermocouple. The reason is that the output voltage is very small in the range of millivolts. So for 100 degrees Celsius change in temperature, we'll get an output voltage of few millivolts. So few millivolts per 100 degrees Celsius is the sensitivity of a thermocouple. So see the sensitivity. It's such a low sensitive device, thermocouple, where thermocouple is actually used where temperature variation is very drastic or very vast, because for 100 degrees Celsius variation you can expect only few millivolts. So to get a higher value in millivolts, you require a very large variation in temperature, and that is why thermocouples are used for wide temperature range applications. Okay, and we have to use electronic circuitry along with thermocouple so that we can get we can strengthen the voltage. So today we'll see the next class of temperature transducers, that is thermistors. So thermistors has an expansion as thermal resistors. So it is another simple passive device. So they are actually made of sintered ceramics. So what is the meaning of sintered? The meaning of sintered is that powdered thing which are formed or molded in the form of solids. So ceramics, we know they are actually first in the form of powder, they are processed and molded in various shapes. So they are sintered ceramics, usually from mixtures of oxides of iron, manganese, nickel, cobalt and copper, and they are mainly formed in the form of beads or discs. So this is actually what about the construction, how the thermistors are constructed, and their resistance may range, variation resistance may range from 100 ohms to 100 kilo ohms, and their characteristics, temperature change, the resistance with temperature change is highly nonlinear, that is exponentially decaying curve, we'll see that, and this is our basic equation, that is resistance RT of a thermistor at any temperature capital T can be expressed by the equation A into e raised to B by T. Okay, so if we have two temperatures, we have two temperature differences, that is T1 and T2, then this will be 1 by T1 minus 1 by T2 multiplied by B. So B, A and B are constants. So what is R2? R2T. RT2, sorry, RT2. RT2 is nothing but the resistance at some non-temperature T2. So this T2 is the reference temperature. So if this resistance at this reference temperature is non, then you can identify the temperature, the resistance at the temperature T1. So you get the temperature at T1. From here you can get the value for T1. So the known values will be the temperature T2, the unknown value will be T1, and as T2 is known, you can find the resistance at the reference temperature, so that by this equation you get this value. If this value is resulted, then you can get the value for T1. That is how you get the value for unknown temperature using a thermistor. Now we'll see the characteristics. I told that this is a highly nonlinear characteristics. One thing is that its temperature coefficient, resistance temperature coefficient, is negative. Unlike metals are having positive temperature coefficient. The meaning is that if it is positive, along with increase in temperature, resistance also increases, whereas if it is negative, along with increase in temperature, resistance decreases. And that is evident from this graph, where you see that at minus 100 degrees Celsius, the resistance is maximum, or in the range of 10 raised to 6 ohm. So resistivity, we have taken the resistivity. So this is having maximum resistivity of the order of 10 raised to 6. Whereas when we reach 0 degrees Celsius, resistivity is in the order of 10 square. And when we come back, or when the temperature increases, or when it go beyond 400 degrees Celsius, the resistivity decreases to a value of the order of 10 raised to minus 2 ohm meter. So this is actually the characteristics of a nonlinear exponentially decaying characteristics of a thermistor. Okay, so this is the important thing is that this thermistor is having negative temperature resistance temperature coefficient. And when we compare this one with a platinum, so platinum, it is having more or less a constant resistivity over a wide range of temperature. That is why we always compare any resistors with platinum. Platinum is having that is one quality of platinum, that is highly constant resistivity for maybe for from 100 degrees Celsius to 400 degrees Celsius, its resistivity is almost a constant. That is why we compare it with thermistor. Okay, so now another important, any two-terminal device will have its own VI characteristics. So thermistors also have VI characteristics. So this is my VI characteristics, voltage against current. You can see that at 0 degrees Celsius you have maximum voltage, and the current is somewhere in between 10 raised to minus 6 and 10 raised to minus 5 amperes. Now as the temperature increases, that is from 0 to 60 degree, you can see that voltage decreases. Voltage has come down, but the current has increased. At this point, voltage has come down and the current has decreased. Now at this point we have again the peak here, that is again the voltage as we increase the temperature, again this is 60 degrees Celsius and this is 25 degrees Celsius. So again when the temperature increases, voltage dips but the current increases. You can see that current is now the current peak is between 10 raised to minus 4 and 10 raised to minus 5. Okay, so this is actually so you're getting a family of curves which shows the VI characteristics of thermistor at various temperature. When temperature varies, what happens to voltage and current? So what is the inference? As temperature increases, resistance value decreases, so that current value increases and thereby voltage dips. So that is another characteristics of the VI characteristics of thermistors. So in general, thermistors, unlike thermocouples, they are having very high sensitivity. So sensitivity in the case, that is their resistance varies. You can expect very high resistance change, very high. That is, suppose if you consider room temperature. Suppose if the room temperature decreases by 1 degree Celsius. Suppose if the room temperature decreases by 1 degree Celsius, then the resistance of the thermistor increases by 5%. See, room temperature decreases by 1 degree Celsius. What happens to the thermistor resistance? That resistance will increase by about 5%. So this is the high sensitivity of a thermistor. So it is very sensitive to temperature changes. That is why, unlike a thermocouple, the thermistor is used for measuring small variations in temperature. Thermocouple, whereas we use thermocouple for large variations in temperature, whereas thermistors are used for small variations in temperature. And that is why the reason is that the sensitivity is very high. Okay, so this is all about thermistors, and next we'll see about the entry level temperature transducer, that is resistive thermometers. And the equation, this is a well-known equation, that is resistance at any temperature can be found out by this equation. Although this is a exponentially growing series, we usually take only the first two terms. We neglect the second order terms so that we'll get we make a linear approximation. Okay, so we'll take only usually these two terms, this much only for linear approximation, where R0 is the resistance at temperature T is equal to 0 or the reference temperature, and alpha, alpha 2, alpha 3 up to alpha n are constants. If we are going for a linear approximation, we take only alpha 1, or alpha 1 is equal to alpha, where alpha is the resistance coefficient, temperature resistance temperature coefficient. Now, what is the material inside a resistance thermometer? So that is having an important quality, that should have some important qualities. That is, the element inside the resistance thermometer is called an RTD, that is resistance temperature detector. RTD, resistance temperature detector. So element present inside a resistance thermometer is called a resistance temperature detector. Two qualities should be there for this element. One is that it should be inert in nature. That is, it should not be contaminated by some sort of chemical reactions. It should be inert in nature. That the meaning is it should not form oxides, metal oxides, something like that. Okay, so it should be inert. That is one quality. And another quality is that the resistance element should have very high resistivity value. Very high resistivity value. So one thing is it should be inert in nature, and next thing is that the element should have very high resistivity. So platinum is one material which is having very high resistivities, and also we know that it is having a constant resistivity also. So it is having a very high resistivity. I'll tell the reason why it should have very high resistivity. And next is that it is almost inert also. It has limited susceptibility to contamination. So it can be treated as a noble metal. So a question arises, why can't we use gold or silver? They are also very inert than than platinum. So gold and silver is also inert. They are more inert than platinum. The thing is that their resistivities are low. So what happens if the resistivities are low? We know that rho is equal to Ra by L. That is, this is actually taken from basic equation R is equal to rho L by A. So R into A divided by L is nothing but the resistivity. So if a material has very high resistivity, the meaning is that the numerator is high. That is, the resistance is the numerator is high, or the length, the denominator is very small. So you can have, for a material having high resistivity, you can have the length of this element very small. You can select very short element, so it actually decreases the overall length of the thermal resistance thermometer. So the high resistive material will actually will be very short in length, so that will overall reduce the shape and size of the resistance temperature thermometer. And one more thing is that all these materials, whether thermocouple, thermistors or RTD, can come in various shapes like disc type, bead type, or glass coated. And another thing is that many industrial transducers will come inside some housings. It can be a glass housing or some other housing. So if that is a protective layer, so if they are inside or housed inside such a housing, they are known as props. So RTDs, thermistors, thermocouples, all are available in props. And you can see that perhaps there are some other materials also which can be used as RTDs, and platinum is most commonly used, and this is the change. That is, for 1 degree change in temperature, this much is the change in resistance. 0.00392, the amount of ohms resistance is changing with respect to 1 degree change in temperature. And we can use tungsten. You can use, this was the point I want to make, that is, you can use tungsten also, but tungsten is used only for high temperature applications because of its extremely brittle nature, and we cannot comfortably work with such a brittle thing. And copper is also occasionally used as RTD element, although platinum is commonly used. Now, the characteristics. I told that we are making a linear approximation, so we are neglecting all the higher order terms. In that case, we compare. This is actually we are making it as a nominal value. That is, we are comparing the resistance with the reference resistance, that is the resistance at 0 degrees Celsius, and comparing with temperature. You can say that at least for small regions of temperature range, small ranges of temperature, it is approximately linear. So this is for nickel, this is for oxides of copper, this is for nickel as the RTD, copper RTD, and this is for platinum. Platinum is, you can see it from the graph itself, platinum is more or less linear for a wide range of temperature. That is another advantage of using platinum as RTD. Okay, so this much are the temperature transducers. First one we discussed about thermocouples, and today we discussed about thermistors and RTD. So thank you so much.